Welcome to Calculus. Today we will investigate integrating definite integrals by substitution. We'll take a look at 3 examples total. Our first 2 examples want us to find the definite integral's value in 2 different ways. The first way is to find the related indefinite integral and then to put back my limits of integration and evaluate using fundamental theorem of calculus. And then the second way is to make a substitution in the integrand and change the limits of integration. Well, let's investigate this first example in those 2 different ways. So our integration first is from -2 to 0 of the integrand x over x squared plus 3 squared dx. I want to treat this as an indefinite integral first. That's the first strategy. So what I'll do is I'll just consider this as an integral without limits of integration. And I want to integrate this using substitution. The part that I want to substitute is this x squared plus 3. That's what I want to define as my u. So we'll do that first. My u here is going to be x squared plus 3. So we'll find our du, and that's going to be 2x dx. So just comparing my parts to the pieces that I've got both in this du and in the original integrand, I've got the x, I have dx. What I don't have is the 2. So I do need to include another coefficient to cancel the 2. I'll put a half there, and it's going to show up in front. So my half du is going to be equivalent to x dx. So we'll make that substitution. Again, we're treating this as an indefinite integral first. This is the initial strategy that we've got. So here I'm going to call it the integration of 1 over u squared du. And I'll place that half out front that I put out in front of half du there. And then I want to integrate. So this is going to become 1/2. And then this u to the power of 2, if it's in the denominator, I can treat it like u to the power of -2. So the antiderivative for u to the power of -2 would be u to the power of -1. But I need to include a -1 over 1 to cancel that, since I have no coefficient here in my integrand. Plus c, since currently it's an indefinite integral. So what I want to do now is substitute back in my value for u. So this is going to become -1 over 2. And then I'll go ahead and put u down here in the denominator. I'm substituting back in x squared plus 3. That's how I defined u. Now, once I make that substitution back in, I now want to treat this as a definite integral and evaluate according to the fundamental theorem of calculus, which says basically this is equivalent to the function here evaluated at 0 minus the function evaluated at -2. So we'll do those calculations. This is going to become -1 over 2 times 0 squared plus 3 minus -1 over 2 times -2 squared, put that in parentheses, plus 3. And then we want to evaluate. So down below, I've got 2 times 0 plus 3 is 6. So that's -1/6. My double negative will turn into a plus 1 over, I'll start in here in the interior, -2 squared is 4 plus 3 is 7 times 2 is 14. And if I add -1/6 plus 1 over 14, that is going to give me -2 over 21. So that is calculated in the first way. Again, I took off my limits of integration, integrated it as an indefinite integral, and then put the limits back, evaluate according to fundamental theorem of calculus. So we want to try the same task with a different approach. So the second approach is to keep basically my same substitution. So I'm going to go ahead and write 1/2 times the integration of 1 over u squared du. But what I want to do is I want to bring back the way I defined u. Again, that's x squared plus 3. And just to see du here, that's 1/2 times 2x dx. Now, all that's the same. What changes at this point is I actually want to include limits of integration, but they need to be evaluated within the u substitution. So what I'm going to do is I'm going to evaluate u at 0. And basically, I'm just going to take the way I've defined u is x squared plus 3, plug in 0 for x. So that's going to be 0 squared plus 3. And I'm going to evaluate that. That's 3. So my new upper limit of integration is going to be positive 3. We'll do the same for the lower limit of integration. So there I want to evaluate u at negative 2. So that's going to give me negative 2 squared plus 3. And that's going to be 4 plus 3 or 7. And at this point, notice I've changed my limits of integration just by running my original limits of integration, which were defined in terms of x, here through my u function, which is really the way I set up the substitution. Now I should get the same value, negative 2 over 21. So let's integrate again now with this second version. The nice thing here is I don't have to make a substitution with my x squared plus 3 back in here. I just am going to treat this all the way with u. So let's find the integration. So that's going to be 1/2 times the integration of 1 over u squared. That's 1 over u to the negative 2. It's going to look just like our original. So it's going to be negative 1 u to the power of negative 1. But then I stop and I just want to integrate from 7 to 3. Now notice my larger value when I change my limits here is below, but it should work the same. So I'm just going to run it the way it's presented. So this is equal to negative 1/2. Really, it's negative 1 over 2u from 7 to 3. So let's evaluate here. Notice again, I'm not putting any of the x squared plus 3 back in. I'm just dealing with the u. So it's negative 1 over 2 times 3 for my upper limit of integration minus negative 1 over 2 times 7. And that's going to give me negative 1 over 6 plus 1 over 14, which is exactly what I got before. Going to yield negative 2 over 21. So we get the same evaluation in both strategies. Again, the first, treating it as an indefinite integral and then evaluating according to the fundamental theorem of calculus. The second one, changing my limits of integration. Our second example is this integration from 0 to 2 of x times 3 to the power of 2x squared dx. So I want to try this again in the same two ways. So I'll start off with this example. Again, I want to identify the part that I want to substitute with a u. And that's going to be this power 2x squared. So we'll call that u initially. And we'll find du here is going to be 2 times the old power of 2 is 4x dx. But I don't see a 4. If I check at this point for the parts that are there for the substitution, I've got the x and the dx, but I need to cancel that 4 out. So I'm going to multiply by 1/4. and that'll ensure that that matches my original integrand. So let's approach this in that first way. So again, I'm going to take this and now treat it as an indefinite integral. And let's make the substitution. So it's going to be 3 to the power of u du, but then I need my quarter out front. Just like our previous example, at this point, I want to integrate and treat this as an indefinite integral. So it's a quarter. And then to integrate 3 to the power of u du, that's going to be 1 over the natural log of 3 times 3 to the power of u plus c. Again, I'm putting the plus c because currently we're treating it like an indefinite integral. I want to substitute back in then my 2x squared for u. So this is now going to be, if I bundle these two fractions, 1 over 4 times natural log of 3 times 3 to the power of substituting back in 2x squared. And at that point, I want to replace my limits of integration from 0 to 2. So I'm converting at that point from indefinite to definite integration, and we want to evaluate. So this is going to be equivalent to 1 over 4 times natural log of 3 times 3 to the power of 2 times 2 squared minus 1 over 4 natural logarithm of 3 times base 3 to the power of 2 times 0 squared. I can calculate this in a couple different ways. I see I've got this 1 over 4 natural log of 3 as a factor in each term. So I could factor it out, and that would be equivalent to this 1 over 4 natural log of 3 times 3 to the power of 8 minus 3 to the power of 0. And then 3 to the power of 8 is going to give us 6,561. 3 to the power of 0 is just 1, so that's 6,560. And I can place that in the numerator of my fraction over 4 natural log 3. But then if I divided 4 out of 6,560, that would leave me with 1640 over 4 times the natural log of 3. So the first strategy gets me to that evaluation. Again, what I want to check is to see, do I get the same evaluation if I change my limits of integration? So just as in our previous example, what I want to grab is this u substitution we done here in the purple. But I want to pick it up. So let me write it here. It's a quarter times the integration of 3 to the power of u du. And again, we're using u as a substitution for 2x squared and a quarter du to represent 1/4 times 4 times x dx. And again, it's just the x dx that's showing up in our original integrand. But I want to now convert my 0 and my 2, my limits of integration. So I want to evaluate u at 2 for the upper limit. So that's going to be 2 times 2 squared, which is going to be 8. So I'm going to place that as my upper limit of integration. Now it's scaled or evaluated for the u function. Let's also do so for u at 0, my lower limit of integration. So that's 2 times 0 to the power of 2, which is just 0. So I'm ready now to evaluate this. Now, just in terms of u, I will never revert back to an x expression. So this is going to be equivalent to 1/4 from that outer coefficient times 1 over natural logarithm of 3 times 3 to the power of u. and evaluated from 0 to 8. So now I'm ready to evaluate. This again is going to become 1/4 times the natural log of 3. If I combine those first two fractions, so 3 to the power of 8 minus 1/4 natural log of 3 times 3 to the power of 0. And I see that that's exactly the same expression that I've got here. Once I factor 1/4 natural log of 3 out, we can recreate that. That's 1/4 natural log of 3 times quantity 3 to the power of 8 minus 3 to the power of 0. And that's going to give us the same simplified response, 1,640/4. Oops, let me make a correction. That 4 canceled, over natural logarithm of 3. And so again, we're seeing the same result. I can use either strategy. Either treat it as an indefinite integral, make the substitution, and then bring back your x expression and your limits of integration, or run your limits of integration through the u function and change those and then just go with the u function. Our last example is this definite integral from 2 to 3 of 1/x natural log of x dx. So on this example, we just have to find the evaluation of the definite integral. So I want to start off, the tricky part with some of these questions is to know what to define as my u substitution. So I'm going to choose natural log of x to be my u. So I'll make that equation here, u equals natural log of x. So the derivative of u is going to be 1/x dx, and that works out pretty well for us. I've got the 1/x represented. I also have dx represented. So that's really without any need for any coefficients to be incorporated in. So I'm going to approach this one from the second strategy. I'm going to evaluate u at 3 and change the upper limit of integration. So that's going to become the natural log of 3. And then u at 2 is going to become and for our lower limit of integration, as I plug in 2 to my u function, that's going to give me a converted lower limit of natural log of 2. So we can set this up now according to our substitutions. This is going to be equivalent to the integration from natural log of 2 to the natural log of 3 of u. In fact, 1/u, since my u here is in the denominator, du. So that's set up and ready for integration. So recall the integration of 1/u is the natural logarithm of u, and we're going to integrate from the natural log of 2 to the natural log of 3. So we use the fundamental theorem of calculus to find this evaluation. So that's natural log of the natural log of 3 minus natural log of the natural log of 2. And then using the logarithmic condensation rules, if I have a difference here, that converts to a quotient. So that's the natural log of the first argument, natural log of 3, over the second argument, natural log of 2. And that finalizes our evaluation. Thanks for joining for this investigation of evaluating definite integrals by substitution. See you soon.